Hello everyone, I'm here to present about a vibrometer. What is a vibrometer? It is a device that is used to detect any vibration of an object. There are two main types of vibrometer. The first one on the left side is a laser vibrometer, and the second one on the right side, it is a vibrometer based on an accelerometer. A laser vibrometer uses Doppler effect to determine the vibration of an object. This is a diagram of a laser vibrometer. We have an object, a photodetector, a beam splitter, and a mirror. As we shoot the laser will hit the beam splitter and will be split into two parts. The first one is the reference beam. The second one is the measurement beam. The measurement beam will hit the object and reflect, become a backscattered light. The vibration in the object will cause the change in frequency and displacement in the backscattered light. As the backscattered light combined with the reference beam become a Doppler shifted light, revealing the Doppler shifted in frequency. The photodetector will process and we can read the vibration of an object. Let's hear out the video.
Laser vibrometry uses the Doppler effect to measure vibrations. If light is scattered from a moving object, its frequency is changed slightly. Within a Polytech vibrometer, a high-precision interferometer detects the minute frequency shifts of the backscattered laser light. To achieve this, the interferometer splits the light into two parts. The so-called reference beam is pointed directly to the photodetector, while the measurement beam is incident on the test object where the light is scattered by the moving surface. Depending on the velocity and displacement, the backscattered light is changed in frequency and phase. The characteristics of the motion are completely contained in the backscattered light. The superposition of this light with the reference beam creates a modulated detector output signal, revealing the Doppler shift in frequency. Signal processing and analysis provides the vibrational velocity and displacement to the test object.
Vibrometer based on an accelerometer. It uses an accelerometer to determine the vibration of an object. For the accelerometer that are used in the device, we will get into the detail later. To use the device, just touch or attach the probe to the object we want to measure the vibration. The vibration will be shown on the screen of the vibrometer. The advantages and disadvantages of a laser vibrometer. It can detect very low frequencies. It is a contactless measurement, which means it does not have to touch or contact the object at all. It is a high accuracy and precision measurement, but it is expensive, low portability. It takes some space and it takes time to set up. For the advantages and disadvantages of a vibrometer based on an accelerometer. It is cheap, small size, high portability, and easy to operate. But it must be contacted to the object all the time, which can disturb the vibration of an object that we want to measure. The vibrometer application. It can be used in automotive, aerospace, material research and testing, acoustic and ultrasonic, medical, and machine inspection. So, which one to pick? A laser vibrometer can detect a very low frequency like bridges or highways. And if you want to avoid any contact to the object, or if you need a high accuracy and precision, a laser vibrometer is a way to go. But if you are on a budget, you want portability, simplicity in the operation, and fast operation, a vibrometer based on an accelerometer is a way to go. Now, let's talk about the accelerometer. What is an accelerometer? It is a measurement device or unit that detects changes in direction. It will send out signals as it experiences an acceleration. For the basic types of accelerometer, the first one is the piezoelectric accelerometer, which is considered as an AC response, which has an output as an alternative current, and it is suitable for a dynamic event. Next is the piezoresistive accelerometer, which is considered as a DC response, which has an output as a direct current. It can be used to measure static acceleration. The last one is the capacitive accelerometer, which is considered as a DC response also. A piezoelectric accelerometer. It works by sending electrical signal from a sudden acceleration acts on it. It uses the piezoelectric effect, which releases electrical voltage or charge when force is applied. Piezoelectric materials that are commonly used are crystal like quartz and tourmaline, and ceramics like barium titanate, lead zirconate titanate, and lead metaniobate, where crystals are more durable and can withstand higher temperature, where the ceramics are more variety in the frequency range and price range. This is an example from a dealer with choice and specification listed. As you can see, there are differences in frequency, impedance, capacitance, the material of the plate, the diameter, and much more. Piezoresistive accelerometer. It works by varying their resistance based on the acceleration they experience. It is very similar to a strain gauge. A piezo element or a piezoresistor is attached to the top or in the cantilever beam. Any deformation change will change the resistance value. Change in the resistance value will be used to determine the acceleration. Commonly used materials are semiconductors like silicon and other metals. Capacitive accelerometer. It measures the capacitance change in the seismic mass under acceleration. The acceleration or force applied will move the mass. As the mass moves, the distance between the gap will change, which causes the capacitance to change, which can be used to determine the acceleration. So, when to pick? If your application is a dynamic measurement application and it is at a high temperature, a piezoelectric accelerometer is the way to go. But if you want a more versatile in terms of frequencies and the application will be used in the static measurement, a piezoresistive accelerometer is a good choice. But if you want a cheap and common, a long-term stability, and great at low frequencies, a capacitive accelerometer is the best. And why not to pick? A piezoelectric accelerometer is not suitable for any static acceleration application. A piezoresistive accelerometer is not suitable to a high temperature application because it is temperature sensitive. It is temperature sensitive due to the thermal expansion of the cantilever beam or the piezoresistor itself, which may cause an elongation and may cause errors and give us false information. The capacitive accelerometer may suffer from poor signal to noise ratio and has a limited dynamic range. For the application, it can be seen in automotive, like in a crash test, in racing purpose, or in other safety purpose. Like on the right picture, it is a picture of a Formula 1 car that can detect G-force that the car and the driver is experiencing. Next, in machines and manufacturing, it can be used to detect a vibration of a machine in order to be able to adjust the vibration absorber of the machine. Next, in buildings and architecture, it is used in a seismic device that can detect earthquakes. Next is the electronic device like your phone. It can sense orientation, vibration, and acceleration. Thank you.
Hello everyone, today I'm going to present about the seismic device. Seismic component devices are widely used to protect bridges from severe damages during earthquakes by absorbing or dissipating input seismic energy. These devices can generally be classified as seismic isolators and damping systems. Seismic isolators reduce peak seismic demand on bridge piers through dynamic isolation of the deck from piers. Seismometers, seismographs, seismograms, what's the difference between them? A seismometer is the internal part of the seismograph, which may be a pendulum or mass mounted on a spring. However, it is often used synonymously with seismograph. Seismographs are instruments used to record the motion of the ground during an earthquake. They are installed in the ground throughout the world and operated as part of a seismographic network. A seismogram is the recording of the ground shaking at a specific location of the instrument. A simple seismograph, sensitive to up-down motions of the earth, is like a wedge hanging from a spring, both suspended from a frame that moves around with any motion detected. A seismograph is a device for measuring the movement of the earth and consists of a ground motion detection sensor called a seismometer coupled with a recording system. Seismographs operate on the principle of inertia. Seismometers used in earthquake studies are highly sensitive to ground movements, so that movements as small as 1 by 10 million centimeters can be detected at the required size. A seismograph is securely mounted onto the surface of the earth so that when the earth shakes, the entire unit shakes with it, except for the mass on the spring, which has an inertia and remains in the same place. As the seismograph shakes under the mass, the recording device on the mass records the relative motion between itself and the rest of the instrument, thus recording the ground motion. What actually moves? This view of a mobile mass is valid if you consider that the frame to which the mass is attached and which is firmly fixed to the ground doesn't move. However, when a quake occurs, or a tremor is produced by any kind of shock, it is actually the ground and therefore the frame attached to it that moves. Application of the seismograph that has P wave and S wave. Here is a short video on P and S wave. Here's a P wave and S wave that apparently show the vibration. The seismic exploration. Geophysics is searching for oil by using seismic equipment. Sound impulses are put into the ground. and the echoes are recorded to measure the subsurface rock layer and find petroleum traps. Modern research seismometers are electronic, and instead of using a pen and drum, the relative motion between the weight and frame generates an electrical voltage that is recorded by a computer.
Earthquakes produce different types of seismic waves that can be identified on seismograms. But did you know that each seismograph station produces 3 different seismograms for each earthquake? Why is that? Doesn't one tell you how big the earthquake was? Earth's movement is 3-dimensional, and one component only reflects one direction of movement. If a station had only one component, you would only know about movement in one direction. Different instruments on the seismograph measure 3 types of motion: up-down or vertical motion, north-south motion, and east-west motion. Let's take a close-up, exaggerated look at how a house would be affected by each direction of motion. When the house is shaken in the east-west direction, this shows up on the lower component. Nothing is recorded on the north-south or vertical components. When the house shifts north-south, this shows up on the second line. When the house is shaken in an up-down or vertical motion, only the top seismogram records the motion. During an actual earthquake, the house can move in all directions. Why is that? Earthquakes produce different types of waves, like body waves and surface waves, and these waves travel out from an earthquake in all directions. Body waves, like P and S waves, travel a curving path through the earth. As a result, they arrive at seismic stations from below. P waves are compressive waves that cause temporary microscopic deformation of the earth in the direction the wave is traveling. Thus, energy is primarily recorded on the vertical component of the seismogram, with less energy recorded horizontally. S waves move more slowly and are more destructive since they advance with a shearing or back and forth motion. Because S waves arrive later than P waves, they're usually seen on a seismogram as a second pulse. S waves cause deformation perpendicular to the direction of wave travel, which is primarily horizontal or back and forth motion, with less energy recorded on the vertical or up and down component. The slower surface waves, such as Love and Rayleigh waves, move in a more complex undulating pattern and thus show up on all 3 components. In conclusion, it is the combination of signals that gives seismologists information about the magnitude, distance, and type of earthquake that occurred.
Advantages: detect lateral and vertical variations in velocity. Produce detailed images of the subsurface used to map stratigraphic units. Response depends on variation in rock density and elastic constants. Disadvantages: large quantity of data is collected. Data is expensive to acquire. Data processing is time-consuming and demands expertise. Equipment is expensive compared to other geophysical methods. Thank you.